Hello everyone, I'm Joseph Kuruvilla, a postdoctoral researcher at University Paris-Saclay. I would like to thank the organizers of this workshop for giving me an opportunity to present the work on three-point Gaussian streaming model and the cosmological information content in relative velocity statistics. This talk will be predominantly based on the work I did with Cristiano Pocciani earlier this year, and the latter part would cover the work I've done with Nabila Ghanem at University Paris-Saclay. The galaxy redshift surveys provide us with a three-dimensional view of the universe. However, the measured redshift is not a perfect distance indicator in the presence of density perturbations. Peculiar velocity along the line of sight distort the actual galaxy distribution, and this phenomenon is known as the redshift space distortion. However, over the last few years, it has proved itself to be a valuable tool to test theories of gravity. For example, on the right-hand side of the plot is a result from the post-DR12 survey, where they have compiled different measurements of growth rate of the structure times the sigma 8 measurement as a function of the redshift. Where we can see the blue band is the Planck cosmology assuming a GR prediction. So here, this provides us with a tool to perfectly test the theories of gravity. And hence, there is a growing interest in RST modeling to extend this kind of analysis to nonlinear scales. Not just that, but also to go beyond the two-point clustering analysis to higher order statistics. So it has been shown that, for example, bispectrum can allow us to have informational gain over power spectrum analysis. So, for example, in the two-point correlation function, one of the caveats is that we need a model which allows us to map from the real space isotropic correlation functions we see on the left side of the panel to the anisotropic correlation function we see on the right hand side panel. So basically, the real space, the isotropic correlation function is what is the unobserved reference frame, while what we observe is the redshift space. And in redshift space correlation function on the small scales, we can see the features coming from the nonlinear effects like the finger of God effect. So one of the ways to map the isotropic real space correlation function to the anisotropic correlation function in redshift space is the so-called streaming model, which was introduced in 1980 by Peebles, further worked on by Fisher in 95 and Scocimaro in 2004. So it tells us that to obtain the anisotropic correlation function in redshift space, it's an integral of the real space correlation function times a relative line of sight velocity distribution. And this relative velocity, line of sight velocity distribution here is denoted by the P2. So the current workhorse is the Gaussian streaming model, where basically the P2, which we introduced in the previous slide, is approximated as a Gaussian, one-dimensional Gaussian distribution. And this was introduced in 95 by Fisher and further worked on, for example, by Reed and White in 2011. And this has been used in several of the surveys, for example, in BOSS analysis and also in several eBOSS analysis, the recent measurements. And there has been various effort in the literature to go beyond this Gaussian approximation to introduce asymmetric velocity distribution, or rather, or even heavier tail than Gaussian distributions. So, however, the question we asked in this work is rather, can we generalize this streaming model framework to three-point and higher order statistics? And turns out we can. So starting from first principle, we derive the streaming model framework for endpoint statistics. And what we get is that it's very similar to what happened in the two-point. What we get is that the anisotropic endpoint full correlation function in redshift space can be obtained as an integral of the isotropic endpoint full function in real space times a joint probability density of n-1 relative line of sight velocity. So just to focus on the case of when n equal to 3, we show that we just want to recap that the full correlation function in 3-point is basically given as here. So it would amount to having a 1 plus 3 sums of the 2-point correlation function with the connected 3-point correlation function. And in the case of the 3-point streaming model, then we can write it as the sum, the full endpoint correlation, the 3-point correlation function in redshift space as obtained by the full correlation function in real space, 3-point correlation function in real space times the P3, which is the basically the velocity distribution for the in the case of 3-point. So now the question we would like to ask is, what does P3 look like? For P2, we knew there was a univariate distribution, and the P3, what we get is basically, we already mentioned it would be an n-1, so we obtain a bivariate distribution. So on the x-axis here, we show the W23 component, parallel component, and on the y-axis we show the W12. On the z-axis here, we measure we show the amplitude of the PDF itself. So one of the features here we can clearly see is that the distribution for this triangular configuration is quite unimodal, and at a quick look, it could be approximated as a bivariate Gaussian, which we will later use in the analysis. But one of the things we wanted to answer is that, however, can we predict the velocity moments of this bivariate Gaussian distribution or bivariate velocity distribution? Turns out we can, and just to show the measurement what we had done from the simulations, on the top panel we show you the configuration we have chosen, where we have fixed 4 sides of the triangle, and where the 5th side, which is basically so the velocity distribution is a function of the 5 separations of the triangular configuration, and we let the R31 perpendicular vary on the x-axis. On the y-axis is basically the mean relative velocity between pairs in a triplet, where the orange color denotes for the 2-3 pair, and for the blue denotes for the 1-2, where the symbols denote the direct measure from the n-body simulation for the matter species, and the blue denotes the prediction from leading order in perturbation theory. So analytically, we can write it as a sum of various pieces of the two pairwise velocity distributions, mean pairwise velocity. And this can also be checked for the second moment, basically the velocity dispersion. And we can see that there is a high fidelity even for above 40 to 50 megaparsec in this plot. So contrary in the case of in the 2-point, there is also a cross momentum because it's a bivariate distribution, and we see that even the perturbation theory is able to predict this also quite accurately at scales greater than 40 to 50 megaparsec. And putting all these things together, now we have the first assumption of what a distribution looked like. So as I mentioned earlier, like just by looking, it looked like a bivariate distribution. As John von Neumann has said, truth is much too complicated to allow anything but approximations. So we wanted to approximate P3 with a distribution, and we chose the bivariate distribution. And we again show the triangular configuration we have chose in the top, and the direct measurement from the simulation is given by the blue contour lines, while the Gaussian distribution approximation with the moments from the leading order in perturbation theory is given by the orange. So we wanted to quantify how if the information is good, or if this approximation is good enough. What we have realized is that through using the metrics like the Kullback-Leibler divergence or the Jensen-Shannon divergence to quantify the information loss, that this approximation is nearly lossless for the scales we have shown for the quasi-linear to linear scales. And for example, at this triangular configuration, the Jensen-Shannon divergence, we obtain a 0.005 nats, where it's bound between 0 and 0.693. So it tells us that the information loss is quite minimal. So now we have all the ingredients we want for the implementation of the 3-point Gaussian streaming model. So where the first is the velocity moments, up from the standard perturbation theory at leading order, the bivariate Gaussian as the approximating PDF for PW3, and also evaluating the real space 2-point correlation function and 3-point correlation function at leading order in perturbation theory. So putting all this together, we show on the left hand side the full 3-point correlation function. Just to remind, the full 3-point correlation would be the 1 plus psi plus psi plus psi plus theta, where theta is the connected, and on the right hand side we show the connected 3-point correlation function. So we have considered, for measuring the left hand side plot, we use the natural estimator for the simulations as given by the blue dots here. That is, the natural estimator would be the DDD over RR. On the right hand side, to connect the connected 3-point correlation function, we use the Sapuri-Saleh estimator, which is as shown here. And the other thing is, here we show the 3 lines. So that is the case A, case B, and case C. So case A is where we basically have the psi coming from the leading order in perturbation theory, and we set theta equal to 0. Case B is where we both use theta and psi, using the 2-point correlation function in real space and the 3-point correlation function in real space coming from leading order in perturbation theory. Case C we varied by taking the 2-point correlation function from Halo model and using 3-point correlation function from the leading order in perturbation theory. So as you can see, basically case B and case C work quite well in the case of, for example, in the connected 3-point correlation function. However, one thing we noticed is that since the connected correlation function in redshift space is dependent on the 5 dimensions, it's quite noisy to measure directly from the simulations. But for the scales we have shown, the model seems to work quite well given the large error bars also. So to quantify, to make it a bit more, to have a higher signal to noise ratio, we looked at some more compressed of the data. So for the first one we looked was the connected 3-point correlation function by spherically averaging basically. So on the left hand side we show the leading order perturbation theory prediction against the measurements for real space, where the two legs of the triangle were fixed as given on the top of the plot, and we're varying the third leg as R31 on the x-axis. And what we see is that already in the real space there seems to be a bit of disagreement with the measurement itself. However, inputting it, now we input that ingredient, the perturbation theory ingredient for 3-point streaming model, and what we get here is the case B. Looking at the case B, that is the blue solid line, we see that the n-body measurements and the predictions from 3-point streaming model works well, especially on the larger scales of 40 megaparsec or so on. And it's also worthwhile to point out the green dashed line, where we computed the 3-point Gaussian streaming model by setting the real space 3-point connected 3-point correlation function as 0. So there is a contribution in the connected redshift space correlation function coming merely from the velocity information, also on the very small scales, for example, in this configuration we have chosen. And another thing we tried to do was to see 3-point correlation function using wedges, which has been used quite for the 2-point analysis. So whereby you compressed according to the angles with respect to the line of sight. Here on this the columns represent basically for the binning for mu12, where we have chosen mu12, that is the angle between the line of sight, and the pair 12, the vector 12 between 0.5 and 1. And on the rows correspond to different angles between the side 2, 3 and the line of sight basically, where the solid lines represent the prediction coming from 3-point Gaussian streaming model, and the colored symbols with the blue and the orange in the top and the bottom row respectively is basically the measurements directly from the simulations. And what we see here is that the 3-point Gaussian streaming model works quite well for this kind of for these configurations we have checked so far. While the full anisotropic, what we showed earlier, was noisy. By compressing it as using spherically averaged or using wedges, we see the measurements with high signal to noise ratio, and the model also works quite well. Now we can ask the question, how what's the dependence on the growth rate of structure for 3-point correlation functions? So here an encouraging thing is that by looking at this, it seems that it suggests that the measuring redshift space 3-point correlation function with sufficient accuracy can help in breaking the F sigma 8 degeneracy, which is present in basically the 2-point clustering analysis. Again, the configurations we have chosen is shown on the top row, basically where which has been given the mean the bin width, the mean of the bin. And on the left hand side of the left panel, we show the full 3-point correlation function and on the right we show the basically the connected 3-point correlation function, and on the y-axis is the growth rate and on the x-axis is the sigma 8. So by varying different parameters, what we see is that as mentioned, there is a suggestion that the measuring the redshift space 3-point correlation function has a different dependencies and can help in breaking these degeneracies. Now, by just varying the growth rate, we show how it is for basically the 3-point correlation function by just varying the fiducial value as shown 0.7 for the blue and 1.3 times the fiducial growth rate. And here also we see that basically the change, there is a variation, and this can help us to constrain growth rate. And so with regards to the galaxy clustering, we can just to give you a brief conclusions for this part of the talk is that to quote the statistician George Box, all models are wrong, but some are useful. And here we have introduced this the Gaussian streaming model for redshift space correlation function, 3-point correlation function, and the ingredients, for example, the velocity moments were predicted using perturbation theory at leading order, and we compared to simulations to show high fidelity for basically dark matter particles here. And we also show how the resulting phenomenological model, the resulting model is quite in agreement with the direct measurements from the simulations. And another in future, what could be done is basically apply this model for the correlation function for halos or galaxies, that is the bias tracers. But in here we use the leading order in standard perturbation flavor, but we could also use more sophisticated perturbation flavors like the CLPT or the cleft, which has been shown to be quite successful in the case of pairwise velocities, or rather the 2-point clustering analysis. Now, just to move on to the thing that, so now we have this velocity, the P3, that is the relative velocity between pairs in a triplet. Now we can ask the question, what is the informational content in this relative velocity statistics? So the main interest comes from the fact that the pairwise velocity, which is the velocity information coming from the 2-point statistics, has been used in basically constraining cosmology from the either to detect a KSC effect, and also can be measured directly from the peculiar velocity surveys to constrain growth rate. So here, to understand the cosmological information content, we use the Fisher matrix formalism. So we measure directly the covariance matrix from the Quixote simulations, which provides us with 44,000 n-body simulations, more than 44,000 n-body simulations. And we also computed the derivatives directly from the Quixote simulations. So this work is in line with basically done by Han et al. This year, where they quantified the information content in Halo redshift space bispectrum using the Quixote suite of simulations. So here, for example, we show earlier, the first part of the talk, I showed how the velocity, the theory, the analytical predictions work for unbiased tracers, that is the dark matter particle. Here I consider halos coming from the Quixote simulations. And here in this plot, we consider all the triangular configurations from 50 to 120 megaparsec. And the minimum halo mass considered here is 5 times 10 to the 13 H inverse solar mass. So the analytical prediction, what we did was to introduce a scale independent but mass dependent bias factor times the prediction, the radial mean pairwise velocities between pairs in a triplet, that as we had shown earlier. So what we can see in the blue line is the measurement from the halos, while the orange dashed line shows the theory predictions times the which includes the bias factor. And for these configurations, we see that this analytical prediction is consistent with the measurement within 5% at max on certain configurations, but for most cases this is accurate within 2% or so on. So this is quite encouraging. However, in this work we wanted to quantify the information content by pushing to the nonlinear scales. Hence, directly using Quixote is quite useful. So just to show how neutrino mass affects this relative velocity statistics between pairs in a triplet, on the left hand panel is basically we show on the color corresponds to the ratio of the R12, which is basically the relative velocity between the pair 1 2 in the triangle 1 2 3. And on the left hand side is basically the left panel shows when the cosmology is the neutrino mass is 0.1 eV, on the middle panel when it is 0.2 eV, and on the right hand side is the 0.4 eV. So on the x-axis is basically we have fixed the triangular side R12 as shown on the top of the plot, and on the x-axis is where the ratio between R31 divided by R12, and on the y-axis is R23 divided by R12. So for example, the top right part of the plots correspond to equilateral configurations and so on. So what we can see is that the neutrino mass, and where of course the fiducial cosmology assumes a neutrino mass to be 0 for the from the Quixote simulation. So what we see is that by taking the ratio, there is a shape dependence for these triangular configurations by introducing neutrino mass. And this is quite good because if we want to constrain cosmological parameters, this kind of shape dependence will be quite helpful. And using the Quixote simulations, where we measured, as mentioned, that the covariance matrix directly from the Quixote, and also the derivatives, the necessary derivatives also using Quixote simulations, we get the joint the Fisher posterior from here, as you can see. So here in this plot, the blue contour lines represents the constraints coming from the mean radial pairwise velocities, and on the orange is basically by with using basically R12 and R23 for halos. And we consider all triangular configurations with a minimum separation of 20 H inverse megaparsec and a maximum separations of 120 megaparsec. Just to focus on the neutrino mass, we see that we are able to obtain a 1 sigma a constraint of neutrino mass of 0.87 or so using just the pairwise velocity information, while using the 3-point relative velocity statistics, we are able to constrain it much more tightly of 0.0654 eV. And this is quite encouraging because this offers us a factor of more than 13 for constraining neutrino mass. And similarly for other parameters also, as you can see, they provide a sizable contribution. The last row of this plot is what we have introduced as a nuisance parameter, which is equivalent of the biasing factor or a scaling parameter here. So including here, we see that this is able to the 3-point relative velocity statistics is able to constrain cosmological parameters quite accurately. Just to take as a takeaway point, takeaway messages from my talk. So I give you 2 points. So the first is that we introduce a phenomenological model for redshift space 3-point correlation function, that is the 3-point Gaussian streaming model. But for checking by checking for the dark matter species or the matter species, we have seen that the model works quite well for the configurations we have checked so far. And on the other hand, that is good for the galaxy clustering, but for other cosmological probes like the KSC effect or the peculiar velocity surveys, we see that the 3-point mean relative velocity statistics also offers a substantial cosmological information gain over mean pairwise velocities. So it would be worthwhile to look into this kind of higher order relative velocity statistics in future surveys from peculiar velocity or either KSC experiment. Thank you for listening to my talk.